So hi everyone, thank you for having me today. So first, let me say that I realize that I may come across as the party breaker here because everybody's excited about big data, and here I am talking about the limitations, right? I'm hoping not everybody thinks this way, but even if everybody does, actually it's good because I think this is meant to be kind of thought-provoking. So it's good I'm grabbing your attention. So my name is Jennifer, and so I'm part of a group at WalmartLabs called the Search Algorithm Team. And so when you're a data scientist in retail, you know all too much about big data, right? I mean, so you have lots of different types of data. You have images, you have descriptions, titles, customer engagement, you can get surveys if you want. Actually, you have lots of data and probably too much of it. And so we're all there because we're excited about big data. So of course I'll talk about, where we are at today, why big data is exciting, but also try to cover the different kinds of problems you may come across when working with big data as a data scientist. All right, so I'll divide my presentation into 4 different parts. So first, I'll obviously confirm that big data is on its way. It's already there, and it looks like we are going to have to deal with it. So I'll show how we can do amazing things with it. But then I'll spend some more time describing what I call the anatomy of a data set. How do you describe the quality of your data and the value of your data? Because I think it's kind of important to follow the rest of the talk. And then I'd like to spend some time balancing, this question that a lot of data scientists and data engineers have brought forward. What is more important, having more data or having better algorithms? And so I would like to, bring a few points over here. And then I'll actually dig into the limitations themselves and show you that even though we're excited, there are a few things we have to be careful about. So let's get started. So obviously, big data is the new norm, right? I mean, a few years ago, I think, we considered big data a buzzword. I wouldn't even call that a buzzword anymore because it's everywhere, right? I mean, so this is our daily lives as data experts. Actually, we're in a phase of unprecedented data explosion, right? I mean, so I don't know if everyone is aware of that number, but like every 1.5 to 2 years, we're actually doubling the size of data we have. So essentially, that means that every 2 years, we are creating as much data as the rest of humankind before that point in time, which is kind of amazing. And so why are we creating so much data now? It's not because we're more active, it's because we're more connected. Now, I mean, every single move you're making, I mean, can be recorded by a smartwatch or by any kind of wearable device. And so, of course, this is a huge opportunity for industries to, try to capture this data and try to make sense of it, and of course, try to monetize on this. But let's take all of this with a grain of salt. So actually, when I say there is an explosion, some of it is actually due to the fact we're capturing data that we may not actually need, or that can maybe, not actually contain any useful information for us. And also, among the data that we capture, there is also repetitive data, so things that we copy over and over again. Anyhow, we're absolutely data obsessed nowadays, and that is for better or for worse. So how come we're seeing such a huge increase of the amount of data we're capturing now? And so the answer to that is obviously we have the technology to do that now, right? The reason why we didn't do it before is not necessarily we were not interested, it's simply that we didn't have the means to do it. Now we have ways to capture data in suspected ways, and we also have the science to try to make sense of it and process it. So a quick fun fact, actually. So I absolutely had to put that in my talk. I mean, because this is the kind of information you can share with your friends and brag about how much knowledge you have, right? I mean, so do you think that data as a weight? And so there was actually a person on YouTube that tried to answer that question a while back. And so by actually considering the fact that data is actually a set of electrons in motion, and by using E equals mc c², you're actually able to compute that the entire of internet in 2005 is the weight of a strawberry. So it's kind of surprising because it's small, it's really small, but at the same time, it actually shows you that data has weight. And so I actually realized that this was for the internet in 2005, right? I mean, so because data is growing, I had to refresh that information. And so as for today, if you take all the data in the world, I would actually approximate that to, like about the weight of a watermelon. And by 2020, you would have basically the weight of a person, right? So why did I actually, share that with you? For 3 reasons. One, data is tangible. It's more tangible than you think it is. The next thing is that we're growing really fast, right? I mean, talk about weight gain. And so finally, I mean, there's still a lot of room to grow. I mean, so at the end of the day, it doesn't look like it's so huge, right? Okay, so let's go back to the technicalities, right? So we all talk about growing the amount of data. So what does growing data actually mean, right? So obviously, as I was mentioning before, this may mean that you may want to collect data in new ways and collect new data sets, exotic data sets. Most of the times, this is not what happens. What happens is you're doing exactly the same thing, you're just doing it at scale, and you're getting more data, more of the same kinds of data. So there are 3 ways to do that. The first thing is you actually increase the number of rows, right? So for a company like Walmart, getting more rows essentially means getting more customers. And so this pretty much happens in an organic way. I'm not doing anything as a data scientist to get more data. It just happens, right? I mean, so hopefully marketing is the reason why we have more customers, but at the end of the day, I'm just waiting for this data to get to me. Then you can increase the amount of data by increasing the number of features, right? I mean, so again, for Walmart, the number of features may be simply increasing the number of items, because I consider, like the way that the customer interacts with an item as a possible feature, right? Or it can also mean that now I'm trying to instrument things that I was not instrumenting before. So for example, if we start showing ads, you also have to account for the behavior of the customer when they interact with these ads. So it can both happen organically, or it can happen because you want to collect extra data that you think is meaningful for the problem you're trying to solve. And then the third way is actually by increasing density, right? So I know what some would say that this is actually increasing the number of rows, right? Just to give you an example, if I think of filmography, increasing the number of rows would actually be looking at a longer clip or a longer movie, right? Increasing density is actually increasing the number of pictures per second. And so there is a notion of like acting faster, right? So again, for Walmart, this may mean that I may want to be more involved with the customer. We used to look at the way the customer is entering a query on the search box just at the moment they actually enter search, and you don't know what happens before. Now, because we're entering in this phase of big data, we have an opportunity to actually see how quickly they're typing, how many times they change their mind, and these kind of things. So at the end of the day, when you grow data in all directions. And so if you increase the number of rows, you're basically expecting to have a scalable model, right? I mean, you take the same models, you're just trying to make them more scalable. If you increase the number of features, you actually want to build a new model. If you increase density, you're expecting to handle your data at a faster speed and reach a level where your models are real time, right? I mean, they're actually able to make decisions in real time. And so it might be more than you bargained for, because it's a lot of work for the data science community, right? I mean, you have to improve your existing models, change your models, think of new ways of capturing and faster way of processing. So it's both an opportunity, but it's also a liability. All right, so there we are today, right? I mean, there are many areas that collect more data and that need a lot of data so that we can actually make progress, for example, in research, medicine, communication, robotics, and so forth and so on, right? And so much data is coming at us. It's both exciting, but it's also mind-boggling. So before we make a judgment call on whether we want this data or not, or if this data is good, I'd like to spend more time explaining how you measure the quality of your data. So why did I use the word anatomy here? So this is because I think that usually when you think of data as an entity, as a vague concept. You don't necessarily think of it as an object that you can actually go and study with precision. And as a data scientist, that doesn't make me feel good. I mean, it essentially says that if a data is just a concept, the data is actually handling me. I'm not handling the data, right? I mean, so I think the fact that you can actually precisely describe your data gives you a feeling of control that the data scientist today has to have. So, so it actually sounds pretty complicated, like put numbers on your data and validate quality. Anyone who's tried to do it actually knows how complicated it is. And just to think about it, anyone who's ever worked with a data set that has more than 10 features and let's say 1,000 rows would know how complicated it is, right? I mean, so the reason for that is as humans, we are attracted by things that we can visualize. So 10 features doesn't seem like a lot from a big data point of view, but it's already too much for the human brain to be able to process easily. So you essentially can describe your data and the quality of your data through 3 different things that need to be accomplished, right? I mean, so there is the concept of sanity, the concept of completeness, and the concept of richness. So I'll explain this concept in just a minute, just so that you realize already, right? I mean, so getting like a very good understanding of how valuable and how good your data is actually something that requires a lot of work, a lot of discipline, a lot of time, the collaboration of multiple teams, and probably the help of artificial intelligence in the future. Okay, so there is a structural aspect to the quality of the data, right? I mean, so there is a concept that you call integrity, right? I mean, so if you look at here, integrity would be something like when I have a specific row that I expect to be, you know, like a specific types of data or specific format of dates, I expect the same kind of, you know, like a formatting across the entire data set. Now, if somebody changes a convention or anything happens or there is a migration of something and people are not careful, this is easily broken. And you would be surprised like how many data sets actually don't even fulfill that, that aspect of things. The other thing is validity. So validity is about variables being in a specific range. So first of all, I don't want to have any crazy values. If most of the time my values are between -10 and 10, I don't want to see, you know, like many values are close to 100. But it also, I mean, it's also more important when you're dealing, for example, with probabilities. I mean, probability by definition is supposed to be between 0 and 1, and it has to say between 0 and 1 for the sanity of the algorithm you're going to build on this. So, I mean, it's really important to make sure that you keep the same conventions and formula and run your data on the same systems over time. The next thing is the aspect of self-consistency. So self-consistency happens, I mean, is important when you work with feature engineering. So we all know that we sometimes don't like to use exactly the data as it is coming, and you want to post-process it, right? I mean, and we know that to be a very efficient way to make our models work better. And so if you use a specific formula to compute a new column, it has to be, you have to understand the same formula and you have to be certain of what that is, right? I mean, and so you may have problems in self-consistency, for example, if part of the data is processed on one system and another part of the data is processed somewhere else. So this is where the process of validation is really important. This is extremely important because it is extremely difficult to diagnose after the fact by a position with a validity and integrity before. And then you have the problem of NAs, right? I mean, so missing data points. Everyone that has worked with this kind of problem knows how annoying it is. So we know that we can try to replace that by a default value, but something that, some kind of fuzzy logic, matching, and try to fill these different holes. But of course, it's not real data, so we don't know how well it's performing, and we don't necessarily understand the biases we're going to get from that. But this is not the biggest problem. The biggest problem actually comes when you actually miss an entire row. And so for us online retailers, that would very easily happen if the add to cart button is broken for a specific set of items. And we may not realize it right away because it's possible that nobody, I mean, it's going to trigger an alarm if it's been like several hours, nobody's buying a specific item that is popular. If the item is not popular, it may take us a very long time to actually figure that out. And so when you actually figure it out, there is no way of fixing it. You essentially have to discard the data. So it's really important to be sure that this doesn't happen. And then finally, you have you have another aspect of things which happens where your data is really clean, it's really good, it looks like everything's perfect, the values are filled, and you think the formats are right. But you may not have interesting information or meaningful information in this data set. And so you would have a situation like this where you have lots of noise. Many of these rows have exactly the same entries. It doesn't look like I'm going to be able to use a lot of this data to do modeling. The problem with that is that depends on the problem I'm trying to solve. If I'm trying to build an anomaly detection system, it may be exactly what I need to see, right? And so there is a definite difference between making the data cleaner and making the data good. I mean, you can have very clean data sets that actually don't have any quality, like value that you can use as a data scientist. So I think it's the right time now to speak about entropy. So entropy is actually the level of randomness you have in a data set. So randomness is good because you want to have like a sufficient amount of information. Entropy is essentially defined by, I mean, it's essentially null if you always have the same value. I mean, you've seen these data sets where you always have the same value. It doesn't seem that you have any discriminative power within one of the values. So maybe it's not worth collecting that specific value. It's actually wasting space. So people are sometimes confused between the difference between variance and entropy. And so let's try to clarify, right? I mean, so obviously both of them try to measure the level of information and randomness that exists in the data set. Entropy is really about how balanced the different values are in a specific data set. So the highest entropy would be reached in a situation where you only have two outcomes, but I mean the data is essentially balanced. This is very interesting when you are trying to build classifiers. On the other hand, if you want to build, some kind of a predictor or something where you actually need to measure the precision of your predictor, you actually need to look at variance, because variance gives you an information of how spread the values within the data set are. Okay, so basically, I mean, the question here is, so what do I want? Do I want to have a data set that has a lot of entropy, or don't I want entropy, right? I mean, so the problem is every signal is actually composed by a data which is actual signal, which I'm looking for, and a noise component. And so I want the signal to have as much entropy as possible, because this is where the information, the discriminative power of my data is going to live. At the same time, I don't want too much entropy in the noise part. And the problem, again, like the notion of noise is problem dependent. So it doesn't look like you can actually do something in advance. It looks like this is something you have to take care on a case-by-case basis. We want entropy at the signal level, and we don't want entropy at the noise level, essentially. So let's try to define the notion of information content, right? I mean, so here I have this toy example where I have these three shapes, and each one can come into one of three flavors, right? I mean, three colors. And so the notion of capacity of storage is essentially like 3 bits, right? I mean, because here I don't have like a binary information, but essentially you need these 3 shapes to be able to define your entire event, your entire row. And so the actual quantity of information is smaller than this, because it has to be contained. So the capacity of storage is, in some sense, the price I have to pay to be able to record that information. Whether that information actually has value is not clear at this point. So there is an algorithm in data mining that actually uses that information, and this is that decision trees. So decision trees work by looking at like successive variables, and they try to see whether once you actually studied variable A, do you still have meaningful information that allow you to separate your data and classify your data just by looking at variable B, right? And so you do that in a successive way, and it's very possible that even if you have a very large number of features, you're just going to have a very small number of features that help you discriminate on the data and make a decision. So just to give you a quick example, right? I mean, so you would have these two data sets here. And so both of them look like they have a lot of entropy and variance for each one of them. But the one on the right actually has a bit of a problem because you have exactly the same values for the second row and the third row. So essentially the third row is 100% described by my second row. So essentially, I'm not interested in that information. I completely wasted this column, right? I mean, so, and this will typically happen in situations where the mutual information is not good and the correlation is really high. So in the same way that variance and entropy kind of show, like describe the same idea of in uncertainty, I mean, you also have the same kind of relationship between correlation and mutual information. Correlation is definitely, like how two variables actually express the same information, right? I mean, so we often think of correlation in a linear way because everybody's used of thinking of the Pearson correlation coefficient, but it can actually be a nonlinear correlation as well, right? And so we have a weird relation with correlation because we want correlation because otherwise we cannot predict anything. If there are no correlations between your output and your input variables, essentially it means that everything's noise. I mean, I don't have any friction that I can actually use to build a predictive model. But we don't like to have too many correlations because we have to handle these in the data, and they're also wasting space. So I mean, in this sense, it's important before I start building a model to try to understand whether I have too much mutual information. If essentially, like, most of my variables translate the same idea, and by looking at variable B, I have very little information compared to variable A, this may be something I don't want to include in my model. So I've described data as a single unit, but in large companies, you have to think of data in terms of an ecosystem. And so this is a common problem in many companies, right? I mean, so you have this master data that someone generates and captures, and then different departments would like to access the same data and use them on their, for their own purposes. So they keep copying that. And so over time, you have this, like a degradation that happens, and so essentially you get something that's completely different from what you had first, and it's very difficult to say which one is actually the most accurate one. So it's something that is going to have a lot of value for companies like mine and many others to actually have one place, which you call the data lake, that actually contains the freshest data. Why is it important? Because you need less engineers. You have less probabilities of making a mistake, and it's easier to go and fix something. It's also cheaper because you can have the same, your Spark can actually live in this area, and you don't have to duplicate like multiple instances of the same programs and the same software. Just like these you would actually call data silos if you actually separate that. And so this is just as dangerous and as bad as people silos in large companies. So at the end of the day, what is good data, right? I mean, so we've seen it's, there are some numbers you can prove around it and some metrics, but at the same time, it's not really easy to really get a sense and be able to say, like, this is good data, I'm ready to use that. The takeaway is, it's important to curate data on its own. It's also important to think of data in terms of an ecosystem. And while data quality is absolute, value is actually contextual to the problem you're trying to solve. So let's switch gears a little bit and talk about why algorithms matter. So all right. Okay, so we've seen an increase, like in the recent years, of algorithms that we call data greedy algorithm, because essentially to function they need a lot of data, and deep learning is the perfect example for that. So why are deep learning specialists excited about big data? So for very one simple reason, there is a statistical benefit from having more data. You're just making the statistical error smaller. And so, but there's also, I mean, this would happen with any algorithm. The reason why for deep learning big data matters is actually you have lots of parameters. And so it's very easy, I don't know if you see the shape of that really well, but basically the more parameters you're going to have and the more local minima you're going to have. And it's very easy for the model to actually fall into this one of the minima through your gradient descent process. And so you would have a situation where you have a bias in your model. And so many specialists actually hope that if you keep increasing the amount of data, you would actually have a convex shape for which it's very easy to find this one solution and actually always converge to the bottom of that. It is not clear whether this is going to happen. I mean, this is a very exciting time for deep learning researchers because we're just at the phase where here, right? I mean, by this line where we're soon going to see whether deep learning actually solve all our problems just by throwing more data at it. So I've started talking about statistical error. So let's try to define that a little bit, right? So when you talk about the goodness or the correctness of a model, you actually have two things you have to look at. You have precision and you have accuracy. So precision is about how precisely, in other terms, how can I put it? Like essentially how sure you are that you're getting the right results. Accuracy is about how true your result is. And so both are really important to get a good model. There is actually a notion of trade-off between these two. And so this is expressed essentially by the fact that you get high variance when your model is too complicated and you're actually overfitting on the data, or you have a high bias when you have not enough parameters in your data. So essentially that means that more data is obviously going to help your precision. But it's not that clear for accuracy, right? Because it may be due to other things like a data imperfection problem. Or it may be that your model is too simplistic and you actually need to throw more features and more parameters at it. Okay, so there are many reasons how, basically many ways for you to fix a model. And so these are actually like the 8 typical things you would do to go fix a model. And out of these, there is one that actually explicitly says that you want to throw more data. The others are essentially transforming your data, trying to do multiple algorithms at the same time. And so at the end of the day, big data is important, but maybe better algorithm and working on your algorithm is just as important. So these are a few, questions that you may have today, that we're so excited about data, but at the same time, there are many reasons why you may ask yourselves why we actually need that, right? So data visualization. We love visualization because it's actually trying to trim some data so that we can actually see the interesting part of it. So while we're worshipping data, we're also appealed by these situations where you can actually get a sense of what your data is, right? Domain knowledge. Domain knowledge is something that all recruiters, when they're actually looking for a data scientist, are actually appealed by having someone, or you're like, for example, Walmart is interested to have data scientists that have experience in retail. If you just throw more data in your models and your models keep performing better, why would you need that, right? And then, there are other considerations, like, Occam's razor is about getting things simpler. Do you actually need more data to do that? And so forth and so on, right? So I'm not going to go through everything. But... All right, so let's dig into the last part, the actual limitations of big data. So the first thing is, so if you look at this example here, right? So you may have a data set where you have two exactly identical rows. And so if I build a predictive model on this, I will actually predict exactly the same value, right? And it's possible that if I'm actually predicting the future, I can actually go check whether I was right or wrong. And it is possible I'm going to find something entirely different, as you see on the right. And statistically, it's not impossible that you would find something so far away from the prediction just because of statistics. But if I keep looking at the distribution and find something on the top right, then I may start wondering, like, how was not able to predict, like, there are actually two different peaks on the distribution. And this is maybe because you're not capturing the right data. So essentially, it doesn't matter how well you model. I mean, I could have kept modeling for days and days and still get the same situation where I just don't get the information I really need to build my predictor and get something that actually works. Sometimes less is more, right? I mean, so I think designers love to use the sentence less is more, but I think as data scientists, it's not necessarily something you would think of. There is actually, I mean, if you look at this curve here, so this is something that psychologists define as being the inverted U model. So essentially, when you put pressure on people, they stop performing well, right? When you don't put enough pressure because there's not enough stress, they get bored. So the optimal functionality for people, I mean, the time they actually perform best is actually somewhere in the middle. If you apply the exact same approach to data scientists, you're going to get the same thing. And so actually, it's very frequent that by getting more data, I mean, data scientists actually get in this, embarrassment of choices kind of situation, and actually the models they stop being as performant. Then there is another psychological argument you could think of. So I mean, this is basically this exponential curve over there is the way that our memory functions. So when we learn something, we lose it really quickly, right? I mean, and so there is this psychologist, Ebbinghaus, that actually discovered that you have this relationship that you want to review the same information several times before you can actually keep it and remind it on the very long term. And so this is how we function when we are preparing for exams. And so for data, it's pretty much the same thing. I mean, if you have this nice chunk of data and you're actually never reviewing it, and in the sense that nobody's using it, then it's going to get lost, right? I mean, people are going to stop. You're going to have employees moving away. You're going to have, if documentation is not good, nobody's going to remember what that is. It's going to get completely lost at some point. So there's a notion of, even if you have really good data and you are not using it, you're essentially letting it die over time. All right, so, and then there's the notion of parallelization. So for me, big data makes me really nervous for one reason. How am I going to process so much more data than what I have already today? And so people always answer parallelization. Unfortunately, parallelization is not infinite, right? I mean, so there is this law called Amdahl's law that gives you a sense of how far we can actually push parallelization. And so just to give you a sense, right? I mean, so it really depends what is the portion of your task that you can actually parallelize, but you also have a communication task that makes things, slower when you actually combine everything back into one answer. And so if you have 95% of your task that you can parallelize, you can actually only speed your task by a factor of 20. So you cannot do that. You cannot keep doing that infinitely. All right, and so this is, basically the cost of big data. So I think people are just we are going to have so much more data to handle, but at the same time, instances are cheaper, memory is cheaper, CPU is cheaper, and this is actually true. I mean, it's really going down really, really, really quickly, and the amount of data we can process is going up. But actually, the numbers are kind of against us, because if you look at the growth of the storage market, so it's going up maybe 5 to 10%. The actual demand in storage is going up by 50%. So I mean, we're actually not really following the amount of memory, storage, and CPU that we're going to need. So we may soon hit a wall where we're going to have to spend much more money to actually be able to handle all the data that we need. And so as data scientists, we are not trained to think of data in terms of money, but I mean, at the end of the day, that's our job, right? I mean, we're in companies to actually make money to the company and make sure that we can help them process the data and monetize on the data. So this kind of questions is going to be very important for us to solve. So is big data really the future? There are two really big problems that I see coming at us. One thing is that there is a problem with labeling. I can get lots of data, but a lot of the data that we're using in retail, and I know it's true of many other places, is actually, some of it has to be manually processed and manually labeled. And so this is a very expensive, very time-consuming process, and it's also like very error-prone, right? I mean, so if you want to use data in the context of a supervised machine learning algorithm, then we're going to have to find a solution for this. The other thing is that deep learning models are kind of what we're hoping to be the next generation of algorithm. But deep learning actually needs so much data because they are very slow learning algorithms. It takes a lot of data to train them because they have a very long memory, right? I mean, so once they are confused by something, it's actually very difficult to erase this part of their memory. And so essentially we have problems where we need thousands of images of a dog to actually teach a computer that this specific image is a dog. When you show 5 pictures of a dog to a toddler or to a baby, they're going to be able to make the difference. And so there's actually a new class of algorithm called one-shot learning that actually help us solve this problem. We're actually able to replicate the way that babies learn. And so they don't need a lot of data. So if these algorithms start performing as well as deep learning, why do we actually need so much data? It's possible that after all, we're not going to need as much data as we think we do. So at the end of the day, I mean, big data alone is not enough, right? I mean, it's really like a place where you have to combine technology with mathematics, the capacity of visualizing something and analyzing something from, you know, like as we do as humans, and also rationality, right? I mean, so I don't think we're at the stage where we can say that artificial intelligence is going to be able to replace human reasoning and human, rationality, of course. All right, so let's wrap up, right? I mean, so this is what I really hope that you will remember from this talk, right? I mean, so we should develop our data, and it looks like we're going to have to figure a lot of things as we go. Our key to success is going to go through being really careful with our data. I mean, like data needs love. I mean, it needs to be processed, and it needs investment to actually like be maintained in a good state over time. Being methodical is really important. We used to define data in terms of the 3 V's, but actually I think that there are new, like now we're thinking of the 7 V's. And so one thing that is really important is value, right? I mean, so if you keep having more data, but you're just copying the same information over and over again, then maybe we don't have as much data as we think we do. At least we don't have as much information. The eternal question between what is more important? Is it data or is it the quality of algorithms? I think it's completely pointless because at the end of the day, algorithms are pretty much data on steroids, given that the data is in the shape that it should be in. So more data is coming at us, and I think we have to get ready for it and be careful what you ask for, right? At the end of the day, more data is good, but better data is best. All right, so I'll just finish with this quote from Goethe. So actually, both content and the method, so the algorithm, actually matter for us to be successful. All right, thank you so much.
Thank you, Jennifer. We've got some time for a few questions.
How did you get the data on the psychological impact of having more data?
So, this is what do you so this is essentially, my experience as a data scientist, right? I mean, at Walmart, I actually saw that our data engineers were always, very eager to bring us more data, and at the end of the day, you really did see that. I mean, at least personally, as a data scientist, I was struggling, I have so much data now, how do I get started? And so that actually involves an extra process where you actually have to pre-clean your data and remove what you think is useless. And unfortunately, most times, what you remove is, because it's useless, is essentially the new features that you just threw in with the hope that it was going to give you such a, a powerful kind of thing. So, just trigger the question at some point, is it possible that, it's the same kind of, at the end of the day, we're humans, right? So a data scientist is still, going through human reasoning, and you're going to have the same psychological factors when you work as a data scientist.